Great. So let me introduce the first paper then. So the first paper we have to start is Learning Physics with a Hierarchical Graph Network. And the authors are Natapong Gentanez, Stefan Jesch, Matthias Müller, and Miles Macklin. So please go ahead.
Hi, everyone. Thanks for coming. My name is Natapong Gentanez. Today I'm going to present the work that I did with my colleague at NVIDIA on learning physics with a hierarchical graph network. So the goal of this work is to learn the material point method with deep learning that support multi-material. So basically, we want to train a deep learning network that predict the effective acceleration for the large time step of simulation that would normally require like many npm simulation substep. And the main contribution of our work are the hierarchical graph network that would allow the information to propagate and be gathered from far away in a single iteration. Obstacle handling that does not require the use of ghost particle, so that we don't need to represent the obstacle as particle. And demonstration that the network can learn multi-material NPM with complex obstacle. And also demonstrate its advantage over previous method like faster training, faster inferencing, lower memory footprint, and also the ability to trade off between speed and accuracy. So let's look at some of result. So the left is ground truth simulation. The middle is our deep learning result, and the right one is the previous work on graph network from DeepMind. And as you can see, the simulation match with the ground truth pretty well. That's another result. So I'll show you more result later if you have time. So the most closely related work to us is the GNS, learning to simulate complex physics with graph network by Sanchez Gonzalez et al. In ICML 2020. So this work uses a graph network and do like several message passing to perform like computation on the network and finally output the acceleration out. And so we mostly compare our work with this paper, as is the state of the art. And so the input to our method, to our network is for each particle, we have a number of features, including velocity of the particle at the previous 5 time steps, the normal of the obstacle in the cell containing the particle, if there is one. Otherwise, it's 0. Like, so we represent obstacle as like a sparse grid. Also, another feature is D, the distance to each boundary clamped to a constant, like in case the scene is bounded. And E is embedding of particle type. So this is to distinguish between type of particle like sand, water, snow. So these features get passed through the network. And finally, the network need to output the effective acceleration, which is just the delta of velocity between next time step and current time step, right? And this acceleration should include all the interaction and collision forces. And when we have it, we can then update the velocity and then use the new velocity to update the position. And so then we have the position in the next time step, and then this can be repeated as needed. And so all of these get normalized with statistic compute from the training data. So this is kind of the overview of the network architecture. We have particle, and then we perform some computation, and then to transfer it to like a sparse grid and at the finest resolution, and then it go to the coarser grid and so on, even coarser grid, and then finally the computation go back from the coarse grid to fine grid and back to finer grid, and finally come back to particle again. So in a hierarchical manner. So the key idea is that we have a hierarchical graph, and the graph node are basically the cell center of cell occupied by particle. And the cell size is R by R by R. This is the same as the interaction radius of particle in the DeepMind work. And then we have a 2 by 2 by 2 cell merge to form the Coarser grid. And the next one we keep on performing the coarsening to get to the next Coarser level. So in step 0, particle feature extraction. So basically, we have the input feature as described earlier, and then we pass it through a fully connected network with one hidden layer, leaky layer rule, and layer normalization to get a latent space encoding with 128 output, essentially. And then we perform a computation from particle to grid, and each particle will be linked to a 8 cell that have a non-zero Taichi interpolation weight. So we perform we pass the feature to the fully connected network, and then accumulate the feature weighted by the trilinear interpolation weight to the cell. And once we have the feature in the cell, we perform a cell-to-cell message passing. This is so that the information can propagate between cells. And we use 4 iteration of message passing in the default configuration. And the message passing is done with the residue connection. For the interest of time, you can see the detail in the paper. I just hope to give you the kind of the high level idea. So the update is done with residue connection so that the feature get refined more and more after each of the message passing iteration. And then that once we have done the message passing, we go from the phi grid to Coarser grid using 8-to-1 coarsening. So again, each of the phi cell is linked to 8 coarse. Eight phi cell is linked to 1 coarse cell. And so this is done with the fully connected network again to compute the feature and then accumulate to the coarse cell. So we do essentially 2 by 2 by 2 merge to go from with like the downsampling size of 8-to-1. So the number of nodes reduced by a factor of 8 in a single pass. And then we perform message passing again, and then go to Coarser resolution again, and keep doing this until we reach the coarsest resolution in the grid. And then we go back from the coarse resolution to phi resolution. Again, by using the fully connected network to compute the feature and then accumulate to the phi grid. And we perform this upsampling as kind of like downsampling as go from the phi grid to coarse grid as a delta update. So the feature that was stored there get updated by the feature from the Coarser grid. So the information is linked by a residue connection, kind of like a unit in the CNN image recognition neural network. And finally, the last step of the computation is to transfer the information from grid to particle. Again, we use a fully connected network with the feature that transfer the information from cell to the particle. And then the result get added to the initial particle feature that we extract in the first step. So that now it get a more refined latent space feature. And the last step is to predict the acceleration from the updated feature. So again, we used a fully connected network to perform this computation from the 128 dimension to the acceleration x, y, and z component. So the loss function that we use is the summing over all particle, the true acceleration, and the calculated acceleration. And we use the Adam optimizer with the learning rate decay from 10 to the power 4 to 10 to the power 6 over 20 million updates. And it uses a mini batch of size 1 frame because we are doing training in 3D. So it's pretty large already for the 4 to 5K particle. And small but critical detail about adding noise to the training data is that we have to correct for the velocity noise, but not the position. If you don't correct for like basically during training, we need to add noise, right? If we don't add any noise to the training, then the network would only see data that very close to the training data only. And if you run inference, the error that get introduced make the simulation diverge from the training set so much that it produces like unrealistic result. So we have to add noise to it, and it need to be done carefully so that the noise added help with the result. Like and what we found is that it only need to correct the velocity error, but not the position error. Otherwise, it's kind of like overcompensate and cause the simulation to become unstable. And we use the Taichi element to generate the training data. It supports both 2D and 3D. We initially test our method with 2D, and once it works, we use 3D and generate a multi-material NPM simulation for the data generation. So now we compare our method with GNS. So the graph size, in terms of graph size, GNS graph is large. Like it basically has particle multiplied by the number of particle within radii, which is 100 to 150. In our work, it's like 8 times the number of particle plus 7 times the number of grid cell, which is significantly smaller. And so the memory usage is proportional to the graph size. So our is much smaller. And also the speed is proportional to graph size. And this is kind of the plot of the training and validation error of our method compared to GNS. And you can see our method is shown in orange. So you can see that during both training and validation set, it tend to be smaller. And for the training time, our method is about 7 times faster. And if partly because the GNS handling obstacle by having ghost particle. And if we don't use ghost particle and use the obstacle handling like us, our method will be still about 3 times faster. And for inference, we are about 11 times faster. And with the obstacle handling, our method is still 4.4 times faster than GNS. And at 40K particle, our method is 3.7 times faster than Taichi element. And more comparison can be found in the paper. So let me show a bit more result. So this is with more particle. So during training, we have about 4 to 5K particle. And this is during inference, we add more particle to the scene. And this is also like with bigger scene, 16 times bigger than the data used during training, and also more particle. And more result can be found in the paper. And this show like